here are my answers to assignment 5. Starting with question 1. The equation x cubed equals 27 has a natural number solution. I got there is an x in the natural numbers such that x cubed equals 27. For part B, a million is not the largest natural number. What I said was there is an x in n, there is a natural number x, which is bigger than a million. Part C, the natural number n is not prime. There is a natural number p, and there's a natural number q, such that p is bigger than 1, and q is bigger than 1, and n equals pq. So there are natural numbers pq, both of them bigger than 1, such that n is the product of p and q. Notice that conjunction splits things in this way. There's a natural order of precedence for the various relationships. First of all, a relationship like equals, greater than, less than comes in. Then you conjoin things and disjoin them and do various other things. And then next in line of precedence is actually conditional and biconditional. And you read these formulas left to right. There's a p in q, there's a p in n, there's a q in n, such that p bigger than 1 and q bigger than 1 and n equals pq. So you read it left right. This is why we made a big deal about that the American Melanoma Foundation, because in mathematics you really have to read things left to right, and the left to right ordering dictates the logic. Okay, well, let's go on to question 2 now. The equation x cubed equals 28 does not have a natural number solution. What I said was it's not the case that there is an x in the natural numbers for which x cubed equals 28. There does not exist a natural number x whose cube is 28. 0 is less than every natural number. By the way, we should remind ourselves that the natural numbers do not include 0. The natural numbers n is the set that begins 1, 2, 3, etc., the counting numbers. And by definition, we exclude 0. So this is in fact a true statement. For all x in the natural numbers, 0 is less than x. I've actually stayed very close to the statement here and wrote 0 is less than x. You might have written x greater than 0. That's fine. The point is, you're saying that all of the natural numbers are to the right of 0. So for all x in n, 0 is less than x. The natural number n is prime. The natural number n is a prime, is to say there do not exist p and q in n which are greater than 1 and for which n equals pq. Okay? This is the negation of part C of the question we just looked at, question 1, right? And so in this case we simply have a negation in front of what we had before. This is what we had in part C of question 1. And we just put a negation in front to get primality. Question 3, everybody loves somebody. Here's how I interpreted that. For all people x, for all persons x, there is a person y such that x loves y. For every person, there is a person they love. The person they love will depend on the person you start with. The y will be different perhaps from one x to the next x. Give me an x, I'll find a y. Give me a person x, I can find a person y such that x loves y. Okay, different people. Again, that American Melanoma Foundation example, which of course is not a problem in real life because everybody interprets it the right way. In fact, some of the people on the forum, in the forum discussions, there were quite a few people who said they couldn't see the problem with the literal statement. Okay, this is why we're making a big deal of this, because to get to the point where you can understand how the ordering of quantifiers can be important, you really have to be able to see what was going on with that kind of example. Okay, let's move on to part B. Everyone is tall or short. What that says is for every person X, either X is tall or X is short. Everybody is one or the other. Actually, the way this works, this is the inclusive or, but of course the properties themselves will make this a disjoint one. You won't have someone who's both tall and short. Although in real life, tall and short will have an overlap. You know, there comes a point where is someone tall or is someone short. So interpreting these is really a matter of interpretation. I mean, I think this is a fairly clear answer, but when you try to map the ambiguous, fuzzy real world into the precision of mathematics, there are some trade-offs. That's the whole point. The point is things like this are very ambiguous. When does tall turn into short? By writing something like this, we've taken something that's ambiguous and fuzzy, and we've forced it to be precise. And that's the whole point of what we're trying to do, to get precision, to get rid of the ambiguity and the fuzziness. Doesn't mean to say that's gone from the real world, but it's gone from our interpretation of the real world. So this is an interpretation within mathematics, if you like, with its precision, of something in the real world which is not precise. Okay, part C, everyone is tall or everyone is short. That actually comes out a different way. That says every person X is tall, that's one part, and the second part, everybody X is short. And here we've got another of these precedence rules for logic, in that universal and quantifiers, or and the same is true for existential quantifiers, as we'll see, theirs are very tight. They bind whatever comes comes next. I mean, so which means we have to use parentheses if we want to use a quantifier that binds everything like we did here. So to make this bind these two, by the way, I'm talking about things like for all X binds the thing that comes next, the thing that's in the parentheses. We use the word binds for quantifiers. That means it governs that. It restricts the X's in there. And the formal terminology for that is binds. And so in the binding rules are quantifiers bind everything that comes next to them. And if you want them to bind a disjunction, you have to put them in parentheses. So that has to become a unit to be bound by for all. Same would be true for exists. In this case, you don't need the parentheses because all you've got is one predicate here, tall X. So you've got for all X, tall X, or for all X, short X. You might ask yourselves, do you need these parentheses here? And the answer is no. I've put them in to be clear. Generally, the rule for parentheses is you put parentheses in when you need them to disambiguate. But because this is the first time we're running through these, I'm being explicit with parentheses. The goal in all cases is avoid ambiguity. And if you haven't got something ambiguous, you don't need the parentheses. All right. So notice that these are different there. This is talking about either everybody is tall or everybody is short. This is highly unlikely to be true, except in a very strange sort of a society. This one is certainly true if we're prepared to say whether tall and short changes at sort of, I don't know, 5 feet or whatever you want to do. Okay. Okay, let's move on. That's enough for that one. Well, for nobody at home, I took it as a sort of a universal quantification, if you like. I read this as for every person X is not at home. You might have gone a different way. You might have said it's not the case that there is an X. It's just at home X. Okay, that would be fine. You might think that this is actually a closer rendering of this one. It depends whether you regard that as some kind of a universal quantifier or not. So I'm interpreting that as saying something about sort of a negative universal quantifier almost. I'm saying it's for all x, it's not the case that x is at home. But you could equally well argue, I think, to say that the most natural one is to say there is no person who's at home. Okay, in natural language, is that a sort of a universal quantification, or is it sort of a negation of an existential quantification? Depends how you interpret it. But both of them are correct. These are equivalent. As we've seen, these are equivalent assertions. So it's just a matter of choice as to which we think more accurately reflects the nuances of English language. Ready? Part E. If John comes, all the women will leave. If John comes, then, so this is, I think, very clearly an if statement, and then there's a conclusion. So this is the antecedent. And then we've got a consequence. So John comes, then it's the case that all the women will leave. For any x, and our variable x ranges over people, so we have to say for every x, if x is a woman, then x leaves. So that's our way of saying all women leave. For all x, if x is, and I've put brackets here because I want to make sure that the universal quantifier applies to this. It's the same x, that if x is a woman, then x leaves. Alrighty, number F, part F. If a man comes, all the women will leave. In this case, it's not a single person, John, it's any old man. So we have to say, if there is an x, so here's the if part. If there is an x who is a man and who comes, then we've got the consequence that every woman leaves. This is the same as the previous thing. So this still says every woman leaves, but instead of saying John comes, I'm saying there is an x who is a man and who comes. Well, in question 4, we're restricted to use variables and quantifiers that only have real numbers and natural numbers. Okay, so we've got two kinds of quantifiers we can use here. The equation, which actually reflects how we often deal with real analysis, with questions involving real numbers. Okay, the equation x squared plus a equals 0 has a real root for any real number a. That would say, and notice by the way that the order is going to change in the way we present these. Here, I've put the universal quantifier at the end, which is very natural in English. But when we interpret it formally within mathematics, we have to put the universal quantifier first because of the way we read from left to right explicitly in mathematical formulas. So I have to say, for every real number a, there is an x, a real number, such that x squared plus a equals 0. When you read left to right, when you have a pair of quantifiers, when you read this, you have to assume that the x depends on a, which we know that. We know that different a's, you have different x that solves the equation. If you have a solution to the equation. I'm not saying these are correct in the sense of true or false. Whether something's true or false is another issue. The focus here is how you express a statement formally within mathematics. And you have to order things left to right so that you get a logical flow. And so there's a dependency. You give me an a, I will find an x dependent on your a, which solves the equation. You give me an equation by giving me a constant a, and I will then find a solution to the equation. Okay, part B. The equation x squared plus a equals 0 has a real root for any negative real number a. Now we've actually got something that's going to be true. Okay. For any a in the reals, and then there's going to be a clause in brackets because the for all a is going to apply to everything that comes next. For all a, if a is negative, then I can find a solution to the equation. Okay, so you give me an a. If that a you give me is negative, then I can find an x which solves the equation. Okay, let's look at part C. Every real number is irrational. Okay, that comes out the following. For every real number A, there's a natural number m and there's a natural number n, such that m equals nx, or in other words, m divided by n equals x. But the x you give me, the x that we start with, might be negative, and these are both positive. So to include the negative numbers, we have to disjoin that with the fact that negative m over n equals x. Okay. Now you could have written it with m over n. I think it's cleaner to write it this way, because the natural numbers actually don't have division. You've got a property of divisibility, but division is not something it's not a defined operation on the natural numbers. What you have on the natural numbers is addition, and you have multiplication. Okay, you don't have negation. You don't have minus. Let's say you can't sort of subtract two natural numbers. You can talk about one natural number being bigger than another one, but within the natural numbers, you only have the two operations: addition and multiplication. Those are the only two operations that are defined on the natural numbers. There's then a question of whether you can subtract, and there's a question of whether you could divide, but those are questions about natural numbers. They're not properties of natural numbers. They're not operations on natural numbers. So with the natural numbers, you only have two operations: addition and subtraction. And so it's cleaner to write it this way. I mean, at this stage in the game, I think it's okay if you wrote it like that. But strictly speaking, if you're talking about the natural numbers, you shouldn't be using things like negation and division. Okay, subtraction and division, that's not what you should be talking about. There are just two properties on the natural numbers: addition and multiplication. Okay, and to allow for the fact that the real numbers can be positive or negative, you have to include the two possibilities, plus and minus. Well, part D is just sort of like a negation of part C, if you like. Okay, and here's how I wrote it. There is an irrational number. So there is a number with the following property: that for all pairs of natural numbers m and n, m divided by n is not equal to x, and negative m divides n is not equal to x. Okay, as before, I have to look at both possibilities to allow for negative numbers. Previously we had a disjunction here because we were talking about the positive thing, and I've really just negated what came before. Notice that I'm not putting brackets around this whole thing because I don't need them, because when you read left to right, there's only one way to read this because of the parentheses I've got in. There is an x in R. This is going to be the irrational number we're asserting to exist, with the property that for all m in n and for all n in n, now I've got brackets in because this part has to be brought together, m is not equal to nx, nor is m equal to negative nx. M divided by n is not equal to x, nor is minus m divided by n equal to x. Okay? So I suggest you compare this one with part C that we just did to see how I've just taken my answer to part C, taken the negation and made it an existence statement. Part E, well, I mentioned when I formulated the question that this one looks quite complicated. It does. Unless you do what I did. There are two ways I answered this two ways. One, I said, well, what I could say is that for all real numbers R, for all real numbers Y, there's a real number that's bigger than Y, which is not rational. So given a real number, I can find a bigger real number. So given a real number, you can find a bigger real number which is not equal to the quotient of two integers m and n. Notice that I didn't bother with the negative part here because I'm going bigger and bigger. And if you're trying to say there's no largest irrational number, you're in the positive range. You're going up into the positive range. So what happens to the left of 0 on the real line is irrelevant. So I don't need the negative part because I'm talking about there being no largest one. But I'm saying that for given any real number, there's a number bigger than that, which is not the quotient of two integers. And again, because I'm now restricting myself to natural numbers, I think it's cleaner to write it in this way. But you don't have to, because globally we're talking about real numbers, which means that we could in fact here just write m over n not equal to x. That would be fine. It was fine before. I'm just trying to draw attention to the point that the natural numbers themselves only have addition and multiplication. But we are, after all, talking about real numbers, so there's no problem writing it this way. Wasn't a problem in the previous questions either. Okay. You could, however, say that this is really a statement about just the irrational numbers. Given any irrational number, there's an even bigger irrational number. Then it gets extremely complicated because you have to say, given any real number r, if that number is irrational, then there's an even bigger number that's irrational. So the difference is, in this one I simply said given any real number, there's a bigger number that's irrational. And in the second one I've said given any irrational number, there's a bigger number that's irrational. Now arguably the second one is a much closer interpretation of what this means, because you could say what this is really saying is it's making a statement about irrationals, so you're really only going to mention irrationals, and that's the second version. Given any irrational, there's a bigger irrational. So this is a closer that's a closer answer. The first one's equivalent to it because the irrationals and the irrationals that make up the reals, they're sort of interspersed, and if you can find an irrational bigger than any real number, then you can find an irrational bigger than any irrational number. But either are correct. It's just a matter of how you're interpreting them and exactly how much of this statement you are capturing in the formalism. Once you've got something formal, it's non-ambiguous so long as you expressed it correctly with the parentheses and so forth. It's not ambiguous. It's absolutely precise. This thing has exactly one interpretation. This thing has exactly one interpretation. That's the whole point. This has several interpretations. I mean, here are two different ones. They're equivalent. They're obviously equivalent for very obvious reasons, but we've cashed them out in different ways. Well, question 5 is our old friend about domestic cars and foreign cars. So C is the set of all cars, dx means x is domestic, mx means x is badly made. All domestic cars are badly made. For all cars, if that car is domestic, then it's badly made. For all cars, if the car is domestic, then it's badly made. I think that's a fairly straightforward one. I wouldn't expect you to come up with anything significantly different from that. In fact, I wouldn't expect you to come up with anything different from that at all. But you might have done. Okay? All foreign cars are badly made. Well, we don't have a predicate for foreign, so we have to take foreign as meaning not domestic, in which case we take the previous one and we just replace the dx by negative dx, and so by not dx. So for all x in C, if x is not domestic, then it's badly made. And here I'm making use of the fact that negation is a very tight binding, has a very tight binding. Negation, like quantifiers, applies to whatever comes next. So if you want to negate a whole bunch of things, you have to sort of join them together and put parenthesis around. in order to make sure that the negation applies to the whole thing. So negation applies to whatever comes next. And so if you want it to apply to a bunch of things, you have to put them in parentheses. So just as with arithmetic and in algebra, you have to use parentheses to disambiguate. And the rules actually follow pretty closely to the rules in arithmetic and algebra. And so once you realize how negation, conjunction, disjunction, conditional, biconditional, once you realize how they correspond to formulas, to the symbols of mathematics, to the symbols of algebra and arithmetic, then you should be able to follow these kinds of formulations. Okay? It just takes a little bit of getting used to, just as it does in arithmetic and algebra. Part C, all badly made cars are domestic. For all cars, if the car is badly made, then it's domestic. Again, I think that one's straightforward. There is a domestic car that's not badly made. There is an X, which is a car, which is domestic, and it's not badly made. Notice, by the way, that when we're capturing universal quantifiers with statements that involve an if-then, then we have a conditional, an implication. For all X, for all X that are in the cars, for all cars, if the car is badly made, then it's domestic. In the case of an existential quantifier, if there is a car, we're saying there is a car which is domestic and not badly made. So when we have universal quantifier, we typically will pair it with a conditional, with an implication. When we have an existential quantifier, we would typically combine it with a conjunction. Okay, so for all goes with the implication, exist goes with conjunction, at least in these kinds of cases. The trick, or it's not a trick, the rule, the thing we have to remember is to try and understand what these things say. So it's never a good idea to look for symbolic rules. That can lead you astray if the formulation is a little bit different. There is a foreign car that's badly made. There is an X in the set of cars which is foreign, namely non-domestic, and it's badly made. And because negation binds tightly, I didn't bother putting parentheses around this. If I'd wanted to say not dx and m of x, I would put parentheses on there. But the negation just binds what comes next to it, and what comes next to it is that it's not domestic. Okay, it's foreign. Alrighty. Well, that takes care of the foreign cars. Let's move on to question 6. Well, question 6 is about the same kind of things we've already been looking at in some of the earlier ones, namely whether things are rationals and whether they're ordered in a certain way, whether they're biggest rationals or whatever. But we've got a different set of restrictions. Here we're asked to simply use quantifiers for real numbers, logical connectives, the order relation, but we do have a symbol q of x, meaning x is rational. So we're going to get a different expression. So the focus in what we're trying to make precise has been put elsewhere. Okay, we're allowed to assume what it is to be rational. That's not part of what we're trying to explicate. So in this case, we don't have to talk about things being in the rails or whatever, because that's all we've got. So I don't have to say for all x in R, for all y in R. I can just say for all x and for all y. And I've left off parentheses because there's no ambiguity. That just means for all x, for all binds, whatever comes next to it. So for all x and for all y. Now I do have brackets because there's a bunch of things going to come next that depend on the for all x and for all y. So for all x and y, if x is less than y, then there's a z which is rational and lies between x and y. So reading left to right, for all pairs of real numbers x and y with x less than y, there's a z which is rational and lies between them. Now I didn't write exists a z in Q. I didn't write that because the Q isn't a set. In this case we've got a predicate meaning that x is rational. Okay, so I'm distinguishing, I mean what I'm doing with a lot of these examples actually is distinguishing between the various formalisms we have for expressing things within mathematics. And sometimes we use sets, sometimes we use predicates, sometimes we use quantifier restrictions, sometimes we use predicate restrictions. They're all different ways of getting formality and precision into statements. And in mathematics, we pick the one that's most relevant. In fact, in most mathematics, we never use these formalisms in this detail. This is much more akin to things we have to write down in computer science. But we're actually trying to unravel, or to learn how to unravel the formal structure beneath the statements we make. Okay? Well, that was number 6. Let's press on to number 7. Okay, and number 7 is this famous quotation, which is allegedly made by Abraham Lincoln. Actually, there's some dispute on websites as to who was supposed to have said this, but it's commonly and popularly ascribed to Abraham Lincoln. For our purposes, it doesn't really matter who said it. The issue is, can we make it precise within mathematical language? You may fool all the people some of the time. You can even fool some of the people all of the time, but you cannot fool all of the people all of the time. The reason I like this example is that the quantifiers in English are used in the way we use quantifiers in English. The quantifiers come at the end of the clauses, but in mathematics we read strictly left to right, and so the quantifiers have to come first. So let's let fxt mean you can fool person, P. That should have been a P, shouldn't it? So let me just change that now. Okay. Let fpt mean you can fool person P at time t. Then let's take these one by one. You may fool all the people some of the time. That means there are some times when you can fool all of the people. There are some times when you can... The point is, taking this clause, the people depend on the time. There are some times when you can fool all of the people. There are some times when you can fool all of the people. So we have to say there are some times when you can fool all of the people. Then there's a second clause, and this is going to be a conjunction because these are different things we're saying. So there's an and, if you like. There's an unstated and here. You may fool all of the people some of the time, and you can fool some of the people all of the time. That's the second part. So and there are some people, and because quantifiers are these extremal cases, we only have there exists and for all, at least those are the common ones. And so some, in the case when we use quantifiers, some is captured simply by there is at least one. And strictly speaking, that's really the logical heart of some. If we say something, then strictly speaking we're saying there's at least one. Now arguably you could say in English, when you use the word some, there's an implication that there's more than one. Okay, well you could follow that, but it turns out that in mathematics it's really more let's just say more efficient to just focus down on one. So there's a specialization occurs in mathematics that when we say some things, we usually mean there's at least one, and we can capture that by the quantifier exists. So you can fool some of the people all of the time. That means there are some people, there's at least one person who can be fooled all of the time. And in this clause, see what's been captured that's important. I mean, you can argue about whether some is really well captured by exists. But really what's going on here is that the people that are fooled can change from one time to another. Okay? No, I said the wrong way around, didn't I? What's really going on here is that all of the time you'll be able to, so for any time you can find some people. Or is that what I was saying? Let me think about this for a minute. So the people all of the time. Yep, I think that's correct. Okay? You can fool some of the people all of the time. So you can find some people who can be fooled all of the time. You can find some people who can be fooled all of the time. Okay, I thought for a moment that when I worked this out a little while ago I got it wrong, but no, I think that's exactly what it means. There are some people who can be fooled for all of the time. Okay, so I'm happy with that one, I'm happy with that one. Let's look at the last one. But the but, that's just another conjunction really. You cannot fool all of the people all of the time. I think this one's the one that's easiest because there's just two alls. It's not the case that you can fool all people all time. And for this one, you could swap those round. You could have for all t and for all p. You've got when you've got two universal quantifiers or two existential quantifiers, it really doesn't matter which order you put them in. But when you have for all and exists, it really does matter which way you write them down. So let's just recap. This says there are times when you can fool all of the people. There are times when you can fool all of the people. The first clause is about fooling all people, and it says that there are times when you can do that. The second clause is different. It says there are people that you can fool all of the time. It's saying there are some people who can always be fooled. You can fool all people some of the time. So there are some times when you can fool all people. And you can fool some people all of the time. There are some people who can be fooled all of the time. But you cannot fool all the people all of the time. Okay, well I stumbled a bit here, or at least I had second thoughts for a moment. But on reflection I decided that I got it right the first time. And I'm happy with those three. So let's, well, I hope you managed to get something similar to that. This is tricky. This is tricky. No doubt about it. That's why it's a good exercise. It's a really good exercise in understanding how mathematical formalisms capture the kind of things we actually do say in the real world. And this is a real world statement, one with some cultural significance. Okay, let's move on to number 8. Okay, well this number 8 is really very similar to the American Melanoma Foundation example. Okay, a driver is involved in an accident every 6 seconds. Okay, so we've got x is a variable to denote a driver, t a variable for a 6-second interval, axt means that x is in an accident during interval t. The headline is written, if we simply take a literal translation from this into the formalisms of this language we've got here, we would say there is a driver such that for all times t, A is involved in an accident at times t, in that 6-second interval. Okay, so that's a literal interpretation. Then we're going to rewrite it so that it's so that the English expression really captures it in a literal way. And then we would say every 6 seconds a driver is involved in an accident. And in that case, we're saying for every 6-second interval, there is a driver involved in an accident. Notice here that the driver can change from one interval to another. The driver can change from one interval to another. For all t, there is an x, axt. These are different. These are very, very different. And this makes a huge difference in mathematics. As I mentioned, a lot of you had trouble really seeing that there was any problem with the American Melanoma Foundation example. And of course, in everyday language, there isn't a problem because we use our understanding of the real world in order to disambiguate. But when you start to make those things precise for doing mathematics, in order to develop a language and a formalism, a way of saying things that's totally precise and reliable, then the order in which you say things makes a big, big difference. And that was the whole point of that exercise and these other ones. It's to make sure that the left-right ordering of the various formulas captures the logical flow. And there's a logic to this. This one says there is a driver who is in an accident every 6 seconds, which is nonsensical. This one says for every 6 seconds there's a driver in an accident. And when we take the formal language, then the distinction is really, really significant. Okie dokie. Well, I guess we've finished. We finished assignment 5. Okay, quite a lot of questions in there. This is not easy to master, but once you've mastered it, boy, you can tear through mathematical arguments at a much greater rate. A lot of the difficulties people have following mathematics is they try to bring to mathematics the inherent sloppiness and ambiguity and vagueness of everyday language. And when you do that, you just run into trouble. The whole point about this formalism is it eliminates all the ambiguity, because in mathematics we very often don't have knowledge of the everyday world to help ourselves out, as we do when we use language in the everyday world. Okay, how did you guys do in assignment 5? Wasn't easy, was it?